Hello everyone, welcome to Canal Physics. In today's video we will cover line graphs, linearization and percentage error. Before we start today's video, don't forget to buy your copy of Physics Foundations. Please click the link in the description below. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Now let's start today's topic. In physics, it's very common to deal with line graphs in a question. Therefore, the equation that is being graphed is in linear form. And if it's not in linear form, we can get it into linear form. And this can lead to the gradient of the line being used to determine a quantity. Let's start with this example where mass is graphed on the vertical axis and volume on the horizontal axis. And over here on the right, we have the formula for density, where the lowercase Greek letter rho is used to represent density, lowercase m for mass, capital V for volume. We saw a similar graph in the error bars video, and we established that the gradient of this line is density. And we justified this by saying that the mass over volume is rise over run, because mass is going to be the rise, being on the vertical axis, and volume is going to be the run, because it's on the horizontal axis. But there's a more sound way to do this, and this is done by getting the equation into linear form. And this is very doable because the graph is a straight line. Now in mathematics, when the straight line goes through the origin, the linear form is y equals mx. There is a plus c term at the end, which is the y-intercept, but c is 0 because the line goes through the origin. Therefore, the y-intercept is 0. All we have to do is match up the variables in linear form to the graph that is being shown. Y is always the vertical axis, x is the horizontal axis, and the constant at the front, m, is the gradient. So what we can do is we can re-express this density equation in linear form. For this example, it only involves one step. All I have to do is multiply v across and I will have my linear form. Now it's unfortunate that lowercase m is used for the gradient in linear form, but also used for mass in physics. So just be careful not to confuse the two. They are different terms. The reason I've lined up the variables like this, m under y, rho under m, and v under x, is that linear form is very apparent now. Because since mass m over here is graphed on the vertical axis, that must be the y term in linear form. And since volume is graphed on the horizontal axis, that must be the x term in linear form. And I'll just write this on the graph itself so it's more clear. So what's left? It looks like the density term matches up nicely with the gradient term. So therefore, the gradient of this line is equal to density. And I'm just going to write this on the graph itself. And I was able to deduce this simply by getting the equation into linear form and then lining the terms up. So with the density example on the previous page, we looked at how the gradient can be used to determine a useful value. But what if the line doesn't go through the origin, therefore the y-intercept is not 0? Well, the y-intercept can also be used to determine a quantity of interest. On this graph, we actually have some values on the axes. And here we've got an equation of motion where v subscript f is the final velocity of an object, v subscript I is the initial velocity, a is the acceleration, and delta t is the time. You might be used to the formula here being written as v equals u plus at, where all the variables mean the same thing. But I guess it's time to grow up now. We now use the bottom one with the subscripts. It's actually more consistent where you've got the same symbol for the same quantity, v representing velocity, but we just use subscripts to represent final and initial. And this delta t here, this triangle t, it doesn't mean uncertainty in time. It still means a value for time or a period of time. We'll talk about why this is the new symbol for time that we use now in a later video. What matters for this video is that we can get this in linear form and get useful values from that using the gradient and y-intercept. For future reference, I'm just going to label my y and x axes. Now from mathematics, when the y-intercept is a non-zero value, in this case you can see it's 3, the linear form is y equals mx plus c. So y again is the vertical axis, m is the gradient, x is the horizontal axis, and c is the y-intercept. Now there's not much to do with this equation of motion to get it into linear form. All I need to do is switch the vi and a delta t terms around. And there it is. I've got this equation in linear form. It was that simple. Now why is this in linear form? It's because vf is being graphed on the vertical axis. You can see here, vf, final velocity. So therefore, that is the y-axis. And this time I'll line it up with arrows. And I can see on the horizontal axis, the x-axis, I've got time, or delta t, in seconds. And that's why I've lined that up with x over here. And we can see that just by lining up the equations, the gradient of this line must be the value of a, the acceleration. And that just leaves the value for c, which is the y-intercept. This must be the initial velocity. And I'll just highlight this on the graph as well. So now that I've done all the matching up, I can actually calculate the value of acceleration and the initial velocity just by looking at the graph. So let's calculate the acceleration by calculating the gradient, because they are the same thing. I've just picked two easy to read points here, which I've highlighted with crosses, and I can see the rise is 2 and the run is 2.5. Therefore, the gradient, hence acceleration, is 0.8 meters per second squared. So it might be good enough to just remember that the units for acceleration is meters per second squared, but these units come from the graph as well, because if the acceleration is rise over run, because it's the gradient, then the units for acceleration will be the rise units divided by the run units. So meters per second for the velocity axis divided by seconds for the time axis is going to be meters per second squared. So that's the acceleration, and now we can use the y-intercept of the graph to determine the initial velocity. And this is quite easy. You can see from here on the y-axis that the y-intercept is 3, hence the initial velocity is also 3 meters per second. And there you have it. By using the gradient and y-intercept of this graph and getting the equation of interest in linear form, I was able to graphically determine useful values. Now let's learn about linearization. Let's start by considering a ball that is dropped from different heights, and the time that it takes to hit the ground is recorded for those heights. The aim is to determine the gravitational acceleration on Earth, and the accepted value is 9.8 meters per second squared. So here we have a little diagram for reference. You can see that the ball starts in someone's hand, so therefore its initial velocity is 0, or v subscript I equals 0. And we can see the height here, h, is the height from the center of the ball, its center of gravity, to the ground. And someone is timing the time it takes for the ball to hit the ground. And that's delta t over here. So here's the data. When the ball is dropped from 1 meter high, it takes 0.46 seconds to reach the ground, 2 meters, 0.65 seconds, etc., etc. So naturally, as you'd expect, as the drop height increases, so does the time to hit the ground. So what we've done here is, on this graph, we have graphed height on the vertical axis, time on the horizontal axis, and you can see the 5 data points here plotted from the table on the left here. And the title of the graph is always the vertical axis name versus the horizontal axis name, hence height versus time. So if you look closely at these dots, a straight line doesn't really go nicely through these dots. I mean, you could do it such that maybe these two end dots are above the line and these other 3 are below the line. But what you'll see here is that instead of a line of best fit or a straight line of best fit, a curve of best fit would be more suitable for this data. And if you look closely, you can see that slight curve in this data. So what I'm going to do is I'm going to add a curve of best fit for this data. So I've tried my best here to draw a smooth curve through these data points. We don't have to rely on just eyeballing it to see whether a curve of best fit is better or not. We can actually look at this equation of motion, which governs the motion of this ball. So here in this equation, S is the displacement of the ball, VI is the initial velocity, delta t is time, half is just a constant, a is the acceleration, and delta t here again, but squared. Once again, you may be familiar with another way to express this equation with slightly different symbols, which is S equals ut plus half at squared. So S is the same, but the other variables are slightly different. Again, out with the old, in with the new, we use this notation now. Now we're going to manipulate this equation so it pertains more to this situation of the ball being dropped at different heights. So since the S is just the displacement, in this situation that is simply the height of the ball above the ground. The initial velocity VI is always 0 because it starts in the person's hand. And since this ball is falling vertically, and of course we're going to ignore air resistance because it is going to be negligible anyway, the acceleration A is simply the acceleration due to gravity, lowercase g. So we know the theoretical accepted value for g on Earth's surface is 9.8 meters per second squared, But the point of this data collection and graphing is to experimentally determine this and see how close we get to 9.8. And this will involve linearization at some point, but we're not going to discuss that on this page. We're going to discuss that on the next page. So given these parameters for this investigation, the equation simplifies to h equals half g delta t squared. Now it's more clear why this should be a curve, because you can see that height h is proportional to delta t squared. So essentially this is a quadratic relationship. And I'm going to just momentarily extrapolate this curve to the origin, because the origin is going to be that theoretical point where if the height is 0, then of course the time is 0. And when I do this, you'll see that it is more obvious that this is definitely a quadratic relationship, as so. But my curves and or lines of best fit should always be within the data, so I'll just remove that again. And just to keep it simple, we will assume that this would go through the origin. Therefore, this equation here, h equals half g delta t squared, has the very simplest quadratic form, which is y equals ax squared. And I've just written these components a little bit spaced apart so it lines up nicely with the physics equation above. So here we can clearly see that h is being graphed on the vertical axis, hence why I've lined it up with y. Delta t is on the horizontal axis, hence why it's lined up with x. And of course you can see the squares over here. And what's left is this half g constant term, which will be this a coefficient. And I'll just put these in different colors to line them up to show you very clearly that this equation is of quadratic form. Here you can see h is graphed on the vertical axis, delta t graphed on the horizontal axis, and this half g constant term is the coefficient a. So I'll just draw a simple sketch of this y equals ax squared form, just to show you how it matches up nicely with our physics graph over here on the left. And this constant coefficient a here just determines how steep this quadratic relationship is. Now we're ready to learn about linearization. Linearization is the process of manipulating data to obtain a linear relationship. So if you look at our table from before, I have added another column here. So all I've done here is got the time values and squared them. So all these values here, 0.21, 0.42, etc., their units are seconds squared because these are time values squared. Just a little recap here of significant figures. Note how I've made sure the significant figures for each row have lined up, because if I'm using 0.46 to get 0.21 by squaring it, I need to make sure the significant figures are the same, because squaring was my operation. And if you're unsure of these significant figure rules, please watch the video on significant figures and scientific notation. But here you can see I've always got the significant figures matching up. 0.79, two significant figures, 0.62, two significant figures, and the only different one here is the last one, 1.02, three significant figures. So therefore the square of that also must be expressed to three significant figures. So this squaring of the time values, that is actually the linearization process done. So why is this linearization squaring the time values? Well, if we just go by direct observation, what I've done here is I've graphed, again, height on the vertical axis, same as before, but now I've got the square of the time values on the horizontal axis. So I'm plotting the first column here on the vertical axis and the third column on the horizontal axis. And you can see these 5 dots now make a really nice straight line, and it seems to even go through the origin. Just to make this more clear, I will draw a line of best fit through these data points. And you see how this straight line nicely goes through the data points, suggesting a linear relationship this time, not a quadratic relationship. Hence why this squaring of the time values is called linearization for this particular investigation. So how does this linear graph line up with our physics equation that produced this graph in the first place? Well, as discussed before in this video, this equation can be expressed in linear form because it is producing a linear graph, so therefore that must be possible. What I'll do is I'll write the quadratic form on top, y equals ax squared, and the linear form on the bottom, y equals mx, so you can see the subtle change we've made. So the only thing I need to highlight here to understand linearization is the delta t term. Because originally all we did was we graphed delta t on the horizontal axis, and you can see how that lines up with the quadratic form. So what you can see from this is that because of this square factor that is still there is a polynomial relationship between h and delta t, hence why we got that quadratic graph when we just graphed delta t. However, if we graph the square of the time values, that becomes our x in the linear form. So our x-axis is the time squared values. And of course, h is being graphed on the vertical axis, so that's y. And this just leaves the half g term, which must be our gradient. So if the gradient of this line of best fit is half the value of gravity, then gravity must be double the gradient. So using the gradient of this line, we can easily determine an experimental value for g. So I'm going to pick 2 points on this line and determine the gradient. I've chosen the points 0.5, 2.4 and 1.04.8. And remember, it's important not to choose points that are the data points. We must choose other points on the line. Therefore, the gradient is equal to 4.8, and a little bit of dimensional analysis tells us that the units of this gradient are the rise units divided by the run units, therefore the units are meters per second squared. And the final step to determine the experimental value of g is to double the gradient. Therefore, g equals 9.6 meters per second squared. And that's it. We will finish this video with percentage error. So percentage error is a measure of how far a measured or experimental value is from the true or accepted value, and this indicates how accurate the result is. So here we can see percentage error is calculated by getting the absolute value of the difference between the experimental value and the true value, and all of this over the true value, and this as a percentage, so times by 100. From this, it's pretty clear to see that if your experimental value amazingly agrees with the true value, so in the example we've looked at with 9.8 for acceleration due to gravity, if 9.8 is what we determined from the experiments, then we would do 9.8 take away 9.8, which is the true or accepted value, and that would of course be 0, and therefore the percentage error is 0, so that indicates perfect accuracy. But this is obviously unlikely in an experiment given the errors that are inevitable. And let's just use the value we got from before with the linearizing and the gradient. And if we recall, we got a value of 9.6, and we know the true or accepted value is 9.8. So let's just substitute this in to see what our percentage error is. And this ultimately gives us 20.4%. Thank you for watching this video. If you found it helpful, please like and share it, and subscribe to my channel for more. Also, click the link in the description below to buy your copy of Physics Foundations. As the author, I guarantee this is the perfect resource for mastering the fundamentals in physics. Ideal for a Year 10 or 11 student who wants to build confidence and improve results in ATAR physics. Thank you.